Oh, sorry, I just noticed that I was muted, and it seems like people keep joining. I hope when they join, you don't hear the ding sound because I keep hearing ding, 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 ding while people keep joining. Okay, I think for the first session, uh, we'll we'll actually start our first session for 50 minutes. Then we'll have a 10 minutes rest, and then another 50 minutes, and then we are done. So I'll start sharing my screen, and I think apparently everyone has the right link. Cool. I'll start sharing my screen now. Let me open my presentation. Okay. Well, actually, I'm trying to move myself around to make sure I do not cover. Okay, maybe we can just uh, show the content. I'm sure that I have previously did this setting. Okay, now it's much handier. Cool. Okay. After too much of technical kind of problems, we managed to share our screen. I'm not sure if you guys see my screen in the full size. If not, can you just text?
Yep, I can see it.
Cool. And it is in the full size, right?
On my
I,
screen,
do, I want.
yes.
Okay, okay. That's very good. Very much. Uh, hey. Hello, everyone, again for the third time. My name is Ali. My full name is Ali Shayiq, and I'm the co-founder of TensorFields, and uh, I'm currently a full-time researcher at University College Dublin. I would appreciate that if people can turn off their actually mics because we hardly get into the session that every single person would need to speak. So it will avoid us to other noises, the surrounding noises also. Yeah, like I said, I'm the CTO of TensorFields at the moment. I have quite OpenFOAM experience, and my current research is currently focused on deformation problems, which is highly sought after in the manufacturing industry. I think I have a video here for rolling simulation, just one of the simple simulations that I do. So quite simple, just a rolling simulation. Uh, so yeah, like I said, the deformations I work on are highly sought after in the steel manufacturing industries, and those steel manufacturing industries serve other upstream industries like oil and gas, automotive, etc. And about TensorFields, it is established around 2 years ago, and it is basically an open form training initiative, but it occurs to us that we do CFD consultancy and physics-based modeling consultancy as well. Uh, we have some services which you can see on our website, tensorfields.com. So the goal of this meeting is to create engineering standard applications. Mostly, well, our focus is C++ and OpenFOAM. The agenda would be, well, to start writing codes in C++, we need to learn a bit of C++. I know most of you have hands-on experience of C++ programming. but we'll introduce simple code, writing simple application and libraries in C++, and we will turn our simple knowledge, let's say, the simple experience that we gain, into a real engineering application, a PDE solver. And we do so by OpenFOAM core libraries, which gives OpenFOAM the strength that it has. So all of you know what OpenFOAM is. This video is really nice. That shows that gives us a bit of sense as to what PDE is. Where did it go? Actually, it is here. Okay. Oh, that's interesting. It's showing it. It's showing an ad. Last time I tried it, it didn't show an ad. Just let me try it once more. Okay, unfortunately, it doesn't like us. I think I have this video here also. Let me give a shot. This is a nice video that shows how a natural phenomena evolves over time from given initial conditions. So yeah, this 3 blue 1 brown is a very famous channel on YouTube. So this video is very nice in the sense that it shows how the turbulence flow evolves given the initial condition. So basically the gist of this video was that PDE is our language to describe the nature, to model the physics, the physical phenomena. This image is maybe it's more understandable. Let's say I want to simulate a deformation problem. I have an object, I apply forces. I know that the deformation is governed, or the displacement of every single point of this object is governed by such an equation. So in finite volume method, one of the solving the PDEs are really difficult analytically. So what we do is that we solve them approximately. One of the methods to solve them approximately is the finite volume method, and it is actually the way that OpenFOAM solves the PDEs. So what OpenFOAM does is that first it discretizes the domain into a number of cells, and then it integrates this equation on every single cell, and we end up with a system of algebraic equations. And then we do it for every single time step until at the end time we reach the final deformed shape. So there are a number of advantages, like OpenFOAM being free and being open source. There are a number of disadvantages also, like poor documentation for sure. For those who want to start, the documentation is poor, but when you get used to it, also when you get used to it at some stages and some libraries, the documentation is poor. And also, open source codes sometimes struggle to fund their work because they need a number of people to work full-time on the source code to maintain the source code, and since the code is available to everyone, no one pays for it. So the revenue stream is also a challenge for them. A very quick introduction on the operating system that we work on. Well, we work on Linux, and despite all other CFD software like Fluent, StarCCM, OpenFOAM doesn't officially has a GUI. We work from the command line, the so-called terminal. And we do everything from a CLI, command line interface, rather than a graphical user interface. Let's get into C++. We will open our terminal and write codes soon, in 1 minute or two. So we'll start with the concept of a function. Let's say you want to make a lemonade. What you do is that, let's say you are the juicer. You get the lemons, you peel the lemons, you cut the lemons, you add sugar, etc. Finally, you return the lemonade. So basically, what we see here, written in the what I said, written in the syntax of C++ is what we see here. You, the juicer, get some input, you do some operations, and then you return the lemonade. So this is the function name. Lemons are the inputs. Anything inside the curly braces is the function body, and you return lemonade, which is your output. So every every C++ application has one main function, one and only one main function. I'll go to my terminal now and actually create a folder, call it 15 December. Okay, and here I want to create a very simple C++ code. I would call it simplest.c, and I will write int main. Okay, what is it? What did we write? Maybe I increase the font a bit and maybe more. Yeah. So the main function is the function that every C++ application must have. It doesn't necessarily get any input. It must return an integer. And what is an integer? An integer is, well, we are talking about the computer doesn't make lemonade. It actually gets bytes and produces another bytes. So byte is the unit of measurement of the memory. You give it input in terms of bytes, and you actually get the function's return in terms of bytes as well. An int is a variable that occupies 2 bytes, depending on the operating system and the compiler, but it is normally 2 bytes. Or for example, double is 8 bytes. So main always return an int. And okay, this simple program actually can be compiled. What do we mean by the program being compiled? Actually, you as the developer, you do not directly talk to the computer. You talk to a compiler, and compiler talks to the computer. Well, to do that, to talk to the compiler, I get back. I actually can show you my screen. Actually, the keys that I hit, so that you see how I use Vim. Maybe you want to use it later. Now I wrote a simplest.c code and I want to compile it. I do G++, simplest.c, output. So the code is compiled. If I show the contents of the current directory, I see that I had simplest.c and I created simplest. I execute simplest, and well, it didn't give any error. Basically, it executed, but it doesn't do anything. So actually, the .c argument, the .c file is called source code, whereas the produced executable is called executable. In some cases, not here, it might be called object code also. The extensions for a C++ code include actually a C++ code. If you are using G++ compiler, C++ code can have a number of extensions, but the one that OpenFOAM uses is capital C. So let's make it a bit more. I think we want our program to say hello. Sorry. Okay, it was interesting. When I open simplest, the executable, it is not human readable. It is just computer readable. But simplest.c is human readable. So what I do here is, let's print out something on the screen. To do that, I write cout, output operator, hello, and go to the new line. And each expression is finished in C++ by semicolon. Okay. For actually, the compiler doesn't know what cout and what this output operator means. To make it known to the compiler, we need to add a header. The way we add headers is the so-called include directive. Using include directive, hash include. I know that the file, the header that includes the meaning of cout and output operator is called IOStream. So what happens here is that on the compile time, the compiler finds this file and put it here. Actually, basically, it is adding this line include something is as if the content of that file is being copied here. So I will do the 𝗏++ command again. It gives me an error. It says the namespace is not specified. What is a namespace? Let's get into the namespace. My first language is Farsi, and there is a word in Farsi called shir, and I'm sure that in every language there are words that has different meanings. A single word can has different meanings. So for example, in Farsi, shir can mean lion. It can also mean milk. How do you understand what the speaker means? Don't forget that we are talking to the compiler. The compiler should know what you are talking about. So you look at the context of the conversation. If the context of the conversation is food, shir means, and if the context of the conversation is animal, shir means lion. Same goes in our code. I open 𝗡𝗙𝗪𝗃 and I say that the namespace is standard. So when you actually these keywords and operators, cout and output operator, are meaningful in the are defined in the standard namespace. Although, well, in the advanced training, you can have your own namespace, and this operator and keywords can do different things. So now, again, 𝗏++, simplest.c, simplest. I'm still getting an error. Give me one sec. Names. Well, it's a bit strange. What was the error? Expected nested specified before namespace. Well, that's really strange,
you
actually.
spelled namespace wrong.
Sorry, I didn't get you.
Namespace is written wrong.
Oh, really? You're right. I was looking for that green color. Cool. Simplest. And yeah, it prints hello. So it's a bit more exciting. Let's get into the next step. I copy simplest into, actually, let us do something here. After the namespace, we get into the objects. Yeah, the objects. Consider a number of students in a university. For example, we have Brian, Jawad, Yanwar. They are actually, all of them are common in the fact that all of them are students. So in the C++ terminology, we say all of the students are the objects of class student. This is the concept of class and objects. This is the concept of one aspect of the object-oriented concept. Not only all of them are students, but all of them have student numbers. All of them have date of birth. All of them has first name. And all of these data are called in OpenFOAM, in C++ terminology, all of these data is called data members of that class. They can do common tasks. For example, all of them can borrow book from the library. All of them are eligible for special discount if they have food in the restaurant on campus. So they have common actions as well, and that common actions is called member functions. This is also the idea of encapsulation, that their common data and their common actions are encapsulated in the class. Let's give another example. For example, you can have billions of circles with different sizes and different colors. All of them are circles. So any single circle is actually a realization of the concept of circle. So the class, all of them are objects of the class of type circle, and all of them has diameter. So diameter is a data member. All of them can has an area. Calculating the area can be a member function. Same goes for the CFD. You can have many different meshes. A mesh around turbine blade, a mesh around a ship's propeller, and so on. The fact that all of them are meshes in OpenFOAM causes them to be an FV mesh object. Any single mesh is a mesh on its own and different from another mesh, but all of them are the same in the sense that they are objects of FV mesh class. And well, FV mesh class has many different attributes. So any mesh has points, faces, etc. And also you can do many operations on the mesh, for example, moving the points. I'll do a very quick library implementation. I think my terminal is very large here. Cool. I'll copy simplest to calc circle area.c. Let's write an object-oriented program that calculates the circle's area. The way we do that is that before namespace, I start creating my circle class. Class, circle, curly braces, and semicolon. This is how you declare a class. Then inside the circle, like we mentioned, a circle can have diameter. So a diameter is, let's say, it is a real number, so it is a double. And I show the data members by an underline after the name because it is the OpenFOAM convention that all data members end with an underline. And I also want an area function that calculates the area. So when the diameter is real, I expect that the area is also real. Area, get a double, which is your diameter, and calculate the area. But we don't say how to calculate the area. So this is in C++, these few lines are called class declaration. So this is declaration, and all class declarations in OpenFOAM are saved into .H files, H for header. And the reason it is called header, I will let you know why. We already know, kind of, because they will appear in the lines like this. They will appear on the top of an application or on top of a source code. Therefore, they are called headers. So we have specified that we want to have a class called circle, but we have not specified how to create that circle, how to calculate the area. First of all, let's tell it how to calculate the area. The notation we use is that circle, actually, what's the area of a circle? The area of a circle with the given length d is pi d squared divided by 4. So in order to make C++ or the compiler know that we are talking about the area here, we need to specify the scope of this function. So we say this function is in the scope of circle. The function is called area, and then this is the function body. This is how you return the area. So you return a double, and so so far so good. The next thing is that I introduced power. Power is defined in another library, which I include here on the top. And well, we haven't specified what diameter should be. Diameter is a data member. The specific function that initializes the data members is called constructor, which basically constructs a specific circle object. By constructing a circle object, we mean we initialize the data members. And then that object has access to all the methods. For example, we have area here. There are a few points. Actually, the constructor is specific in a few ways. First, it doesn't have a return type. It doesn't have a return type. So without writing any return type, we say in the scope of circle, we have a function called what? The constructor has the same name as the class, circle. So this is the second thing special about the constructors. And then we want to actually select, we want to tell our, we don't want always to have a single circle with the same diameter. We want to create different circles with different diameters. So I pass a double diameter to my circle. The third thing special about constructors is the way that they can initialize data members. So The way they do so is colon, then data member, parenthesis, the way you want to initialize it. So here we want to initialize our D underline the data member with the argument D. And the body, we don't need any body here. Simply this piece of code initializes the data member with the argument that we say, and then you have access to the area function. However, I need to declare the function, the constructor here also. Well, it is circle, the constructor, and it gets a, so actually area doesn't need a diameter. Cool. So now the declaration should be compatible with the definitions. We declared area and circle here, but how they work is specified in the definition. Therefore, here are definitions. And definitions in OpenFOAM are saved in .C files. They are also called source or source code. Simply everyone calls in C++ terminology, everyone simply call them sources. So the next thing is anything after class definition is called an application. And applications are also saved into .c files. And actually the main function specifically is called a driver. So what I'm going to do is, forget about hello now. I will create a circle, call it C1. This name is, it can be 1, 2, 3, it can be any other name. This name is not important at all. So you create a circle whose name is C1 and then C1. So don't forget that our constructor, when you create an object, the function that is called is the constructor. And the constructor that we defined needs a diameter. So I pass 2 to the constructor and look at the formula for the area. If I want to calculate the area of a circle with a diameter of 2, 2 to the power of 2 becomes 4, and 4 is simplified by 4, and I'm left with 3.14. Therefore, the results of C1.area is pi itself. To make sure that it is correct, I will show that on the screen. Cout circles area is this. You can write a new line character. You can write end line also. So for now, maybe new line character is enough. So I hope it is clear. We created a circle and we created an area, but we will get an error and we will see what that error is. G++, maybe it is cleaner if I create a calc circle area, move calc circle area into calc circle area. I go into calc circle area directory and G++ calc circle area output calc circle area. So actually, that was the error I was looking for. It says these two functions, both the constructor and the area, are private. This is another note on the encapsulation in C++. And of course, data privacy. A class owns its data and its methods. The area and constructor are not accessible outside the class. When we say outside the class, we mean anything outside these two curly braces and also anything outside the scope of the class. Remember that this colon is called scope operator. Therefore, anything that is not in the curly braces of a class declaration or is not in the scope of the class is private to the class and is not accessible from there. Specifically in the main function is not in the scope of the class. So neither the constructor nor the area are available to us. The way the class let other people to have access to its data is the keyword public. And in OpenFOAM, we normally the coding style is that you intend by 4 spaces. So now if okay, the code is compiled, and calc, if I go for calc, so you see that circle's area is 3.14. So we calculated the area and saw how it works. Now we get into how to compile this program using OpenFOAM rather than using G++. So OpenFOAM has its own compilation system called wmake. The way that, so I remove my binary here, calc circle area, I remove it, and I only have the source code now. If we get time, I will decompose this file into 3 files, and we actually compile the library and the we compile the library and the application separately. I think we have some messages. I'm missing the messages because I'm so actually. Okay, thank you guys. Well, people were talking about my spelling errors, which is very good. Thanks very much. So the next thing is compiling using OpenFOAM compilation system. To use OpenFOAM compilation system, we need a directory called make with capital M. We then inside make, we need a file called files. And inside files, we specify 2 things. The first thing is the name of the source code. The name of the source code is calc circle area.c. And it's going to be an executable. It's going to be an executable, which is saved in foam user application binary, and I'll call it calc circle area. This name here, the name of the binary, the name of the executable doesn't need to be the same as the the name of the source code. But it normally is in OpenFOAM. Well, it's handier, it's more readable, and more easier to follow. Then inside make, not only, by the way, if you wonder what LH means, for those who work on Linux, you are normally you normally know what ls is, which lists with the contents of the directory. I have created an alias for myself so that things are, well, LH knows a few more details and sorts the files in a specific way. Then inside make, I have files. I need another file inside make called options. For now, it needs to be empty, but it needs to exist. So I create that with command touch. That's it. And I simply can run wmake. Sorry, wmake. Okay. I need to say it is OpenFOAM 12. Well, OpenFOAM 12 is the alias on my system for OpenFOAM 12. If you have installed OpenFOAM on your system, you know that at the last step of the installation, normally you can, it is an optional thing, that if you, at the last step of the installation is normally that you make OpenFOAM known to your terminal if you have only one installation. But if you have more than one installations, you need to have an alias, and OpenFOAM 12 is the alias for OpenFOAM for OF12 is the alias for OpenFOAM 12 on my system. Now I run wmake, and here we go. The application is compiled, and it is saved into foam user application binary, and it is called calc user area. We don't need to, you previously remember that I was, the binary was in the same directory, and I was executing that using /calc, etc. We don't have it here now. However, it is in the path that my system, my operating system knows the binaries are there. So simply it means that without /, you can run that command. Which command? The command that we specified in files, calc circle area. And here we go, circle's area is 3.14. Okay, we learned how to work with OpenFOAM compile system. After the session, if you have access to the slides, you will be able to actually do the same thing for a rectangle and calculate the area and perimeter of a rectangle. Actually write a rectangle class, calculate area and perimeter, and compile it with OpenFOAM compiler. This is the solution. So if we get time, we will get into, like I said, we will decompose our simple circle application into 3 different files, into a header file, into a library, into a library source file and into an application. But for now, let's keep it the way it is. And now we get into the main part of the training. We wanted to solve the PDEs, right? So let's get into the math a bit. The way we solve a steady state heat conduction equation as a simple, maybe the simplest PDE that we normally come across is that first, using the finite volume method, first you, let's say your domain is a one-dimensional domain. The right side is cold, the left side is hot, and you want to simply obtain the temperature distribution along this rod. So what you do is that you decompose your domain into a number of cells, then you integrate your equation over every single cell. That leads you to an actually, after using the Gauss theorem, that leads you to an algebraic equation for that single cell, which relates your cell's temperature with its neighbors, like we see here. If you do this process for all the cells, you will end up with a system of equations. So to code that, let's start with discretizing the domain. I will go back, and since finally we are going to make a wave equation solver, I will create a directory called wave. Where are we actually? Okay, wave foam. I create a directory called wavefoam. I go into wavefoam and create a wavefoam.c. So again, I need to write the things that I wrote before, int main. I'll do that quickly. So the way we create mesh in OpenFOAM is, so the simplest mesh is a mesh of type polymesh. So polymesh is a class that creates a mesh for us. We have different mesh classes in OpenFOAM, but for now, to start with, we start with polymesh. I call it mesh. The way actually OpenFOAM mesh is, the easiest way that a polymesh can be created is by reading it from the disk. So I read it from a disk. Well, now we have another class that reads things from the disk and writes things into the disk. That class is called IO object. IO object. I don't get a chance to look at the actually messages. Let me see. I mean, if at any point my sound or my video is problematic, just let me know, please. Okay, IO object is the class that you use to read and write things from and to the disk. IO object has, again, to create an IO object. So look, IO object is a class. It is not an object. So we are going to call an IO object constructor. Basically, we are going to create an IO object. And it is interesting that objects do not necessarily have a name in C++. For example, I'm going to create an IO object here, and it doesn't have any name. It is just fed into the polymesh. That's it. So this IO object, like I said, IO object class has many constructors. The one that we use and we mostly use is, first, we give the name of the objects. The name of the mesh is most of the times region 0. It is hard. This name is hard coded in polymesh class. Region 0, unless we are solving a multi-region problem, and in special cases, the name is different. So after that, after the name, the next thing you specify is where to read or write your mesh. For now, we want to read or write it from the time directories. Runtime.time is the time directories. We have yet to specify what runtime is. Runtime is an object, but we have not created it yet. We will do so. The next thing is read and write options. Is this IO object must this IO object read things from the disk, or is it optional? We want to make it actually forcefully read things from the disk. I think I can, well, I wanted to have my headset, but I don't know if it works now. Just in case people talk to me, I want to make sure that I hear you. Still 1 second. Okay, give me 1 second. Sorry for the interruption. I want to make sure. Yeah, okay, I hear you. Cool. Okay, sorry for the interruption. The read and write options, IO, first, the right option, IO object must read, sorry, first the read option, must read, and auto write. These two options say that you must read the mesh from the memory or you will give an error. And when the mesh changes, you automatically write it into the disk. Actually, this write option is quiet. It is something handy to specify here, but it doesn't force us. You can manage the writing this object outside the constructor also. We will do that. So one thing I forgot is the object registry. Any object that you create, we are creating a mesh here. Any object that you create should be registered. Like assume that there is a registry, there is a book that keeps a record of every single object being created. For the mesh, we use time as registry, run time. This is the OpenFOAM convention. You can play with it and see what other results you get if you register it with some other object. So actually, our mesh construction is finished. Then, like I said, we introduced a few things. We introduced polymesh. We should let our code know what polymesh means. So to do that, I will include polymesh.h. And then we introduced, what else? We introduced IO object. I know that IO object is already included in polymesh, but to be on the safe side, I include IO object also. The next thing is runtime. We have not created runtime. Okay, let's create it then. So with the way we create runtime is a time object. Runtime. It needs a file, let's say Apple, a file name, and a number of arguments, which we call args. So now the time, we need to tell OpenFOAM that, okay, time, what is time? Time is defined in time.h. And so everything is known now. However, on this args, so everything is declared before we introduce it into the code, except args. What is args? In the circle, in the calculation of circle's area, we saw this simple main function, the main function that doesn't get any arguments. You know that there is this standard authority called ISO that actually decides about the standards of many different things. So C++ also has its own standard committee, ISO standard, ISO C++ basically. ISO C++ specifies that the main function is allowed to have two formats only. So the first format is the one that we used in the circles area calculation. The second format that ISO specifies and OpenFOAM uses is int arg count and _arg v. So actually, we don't get into that, what these arguments mean. This simply means that when you want to pass arguments to your function, to your application from the terminal, you need to parse that argument, to interpret that argument, and these actually variables are do that job for us. And the way they do that job for us is using another object called arg list, the list of arguments. The list of arguments gets two arguments. Well, we call it args. We create an arg list object and call it args. And it gets two arguments, argc and argv. Then we are done with the with our args object. I think yeah, the only thing we need to add on the top is arg list. Okay, so I think our code should be compiled now. Like we mentioned before, we need a make directory when you want to compile your code using OpenFOAM compile system. And in make, we have files. In files, we have wave foam.c. And the code is going to be compiled into an executable called exe foam user application binary. And it's going to be called wave foam. That's something. That's one thing. And I need an empty options also. So to make sure that this waveform does not override an existing waveform, I will remove an existing waveform, foam user app binary waveform. Okay. Now I call wmake. Okay. I got a number of errors. There is that. Okay, arg list is not declared. What else? Time was not declared. And polymesh was not declared. That's because we didn't specify the namespace. Using namespace, now the context of the conversation is OpenFOAM. So the namespace is foam. Actually, if I output this into a log, it is easier to debug it. Let me see what error I got. No matching function for call to this IO object. Okay, that's the only error. So I have not used the correct IO object constructor. So it is region. Let me see. Sorry, this is not time. This is name. So runtime name is the name of the time directories. Cool. The code is compiled and I can run waveform. It doesn't print anything. It just asks, okay, go show me the apple in the system directory. Why does it look for apple? You remember that we had apple here, right? So normally OpenFOAM doesn't call it apple. It calls it control dict. Control dict. And then I create a test case. I go inside test. And actually, we will go for a rest in 2 minutes. Just bear with me another 2 minutes. So our test is empty. I create a system. And inside system, I have control dict. And I create a control dict to make sure that this, actually to make this text file, an OpenFOAM file, a file that OpenFOAM reads, we add a header called foam file. And in that, we specify the object. The object name is control dict. And the class, it is a dictionary. And the format is ASCII. If you are using foam extend, you need to actually have version also. And I know that there are a few entries that are mandatory to control dict. For example, delta t, let's say it is 1, and write interval. In OpenFOAM 12, at least these are mandatory. Okay, now if I run waveform, it says, okay, it still looks for apple because I didn't compile the new version. Okay, It's fine. It now asks me to, well, like you saw, we tried to read the mesh from the disk, and it asks me where is polymesh. You asked me waveform wants to read polymesh from the disk. So I what I do is that I copy block mesh dict from cavity. Fluid cavity system block mesh dict into system and block mesh, and now waveform, so it gets executed without any error. Okay, this is good. We will go for a rest for 10 minutes, and then we'll back at, so in Dublin time it will become, so actually maybe 12 minutes. We will be back in 2:40. I'll see you in 12 minutes. Thank you. Welcome back, everyone. Let's start again. So actually, I should go to slide 75, I think. Where were we actually? We were, yeah, let me go to slide 76. Well, for some reason, this is Zoom. Oh, sorry, guys. I noticed that I was mute. Okay, thanks everyone for coming back. We had to continuing. Actually, yeah, I said we are just a bit short in time. I hope everyone can see me and everyone can hear me. I'll try to keep the pace and we'll see what happens. So actually, we could read the mesh from the disk. Let's modify the mesh and write it to the disk. I'll go to Vim, waveform, and I want to scale my mesh and write it into a new time directory. The way I do that is using move points. I say mesh, move, points, move the points of my mesh, actually scale my mesh by a factor of 2. And the way I do that, I say move points to the new points. And the new points are obtained from 2 multiplied by the existing mesh points. So this is just an example of mesh manipulation. I want to show you how this OpenFOAM system works by showing an example of mesh manipulation. So then I say, I want to write it in the next time step. I say runtime ++ and then mesh.write. Cool. I'll go to test, make sure that system, I think I need a 0 directory, but we'll try it. Waveform, here we go. No, we didn't need a 0 directory either. So the directory 1 is created, and I can touch case foam. I show the mesh. Actually, in order for ParaView to show the mesh, I think I need a 0 also. So I create mkdir 0, just an empty 0 directory, so that ParaView shows me the 0, the initial mesh. So maybe Parafoam works because sometimes ParaView conflicts with OpenFOAM Foundation. Did it come up? Yes, it did. So this is my mesh at time 0. I expect that at time 1, it becomes twice. And it does. So from time 0 to time 1. It was just an example of mesh manipulation. You can, actually, you can print other data. For example, after doing so, let's say info. So you remember that we used cout in a standard library. In OpenFOAM, in OpenFOAM namespace, you use info. Info, number of cells is mesh n cells, if I'm not wrong. Yep. And line. So the number of cells is going to be printed here. And actually, I have a 20 by 20 mesh. So the number of cells should be 400. Let's see if it is able to produce that number. I go to my test and waveform. Yes, the number of cells is 400. So our code works. In order to have access to as many member functions as you want, you can have a look at the polymesh class. And virtually, you can call any of the methods in the polymesh class that are public. So vim-foam source, if I'm not wrong, foam, actually OpenFOAM, meshes, polymesh.h, public. Okay, so everything that is labeled as is under the public keyword here can be called through that function that we have. For example, we have okay, actually most of those interesting functions are in another class that polymesh inherits from. The polymesh class actually inherits from the primitive mesh. We didn't actually cover inheritance in this very short course, but it means that when some class inherits from another class, it has access to all the public functions of the other class. So for example, the primitive mesh have a number of interesting geometric attributes. For example, yeah, this was the function that we just called n cells. You can call the number of faces, you can print the number of edges, the number of points, and anything in the under the keyword of public is accessible to you to call through your application. So the next thing is let's get back to our slides. We created the mesh. Actually, again, you can create a random mesh as a just to exercise your developer muscles. Well, if for those who are interested, the slides and the solution to this problem is also available after the course. So the next step is to discretize our PDE. The PDE we are actually going to solve is wave equation. I'll do that here. This is the wave equation. That for some reason is very slow. Well, I don't know why it is not shown up. Maybe here I have a better chance. Excuse me, I just want to show you what equation we are going to solve. Yeah, maybe. Yeah, well, we are going to solve the wave equation, okay? And this wave equation is governed by this equation. This is the very famous wave equation. And the unknown that we are going to solve for is the vertical displacement of the material. And the vertical displacement of the material is expressed by this equation. So as you remember, we discretize during the finite volume procedure, we discretize this equation into a system of equations. And what we solve is actually a system of equations. So we translate a PDE into a system of equations, and that system is actually what we solve. So in OpenFOAM also, we don't create a PDE, we create a system of equations. And for example, one of the strengths of the OpenFOAM is that it mimics the mathematical syntax. For example, for this term, we have d2 dt2u because it is partial squared over partial t squared of the variable u. And FVM stands for finite volume implicit. We want to actually have our unknown in the new time step so that a system is formed. If we assume all of the unknown variables in the current time step, they are not unknown anymore, they are known, and we do not end up with a system of equations. Therefore, FVM is implicit finite volume discretization, time implicit finite volume discretization. Again, for this term, we have the same thing goes on, FVM Laplacian of variable u multiplied by C2. So we'll implement that now. I'll go to waveform and I'll create my equation. The equation is FV. Actually, FV matrix is the class in OpenFOAM that creates that system of equations. Since our unknown is a scalar, I use this notation to specify that it is a FV, it is a system of equations for a scalar unknown. Don't forget that. Okay. This is a system of equations for a scalar unknown. And actually, this notation shouldn't confuse you. You remember, for example, polymesh. FV matrix scalar is also just the name of a class. However, it is a special class. It is called a template class, which we do not get into. Just assume that this whole thing is a single name, FV matrix scalar. And we call it U equation because it is a discretized U equation. And we create that equation based on the syntax that I just showed you. FVM D2 dt2 of U is FVM Laplacian C2 and U. That's it. So a few things. I introduced FV matrix. I need to declare it at the top. Then I introduced FVM. I need to declare FVM also at the top. Then I have introduced the field U, and I have not created the field U. We need to create it. The way we create a field is, in OpenFOAM, the fields are, all the fields that we solve for are geometric fields. Actually, the name of the class that you use to create field objects is geometric field. Geometric field. It is a scalar field for our purpose. Then the second argument is the type of the boundaries. We say FV patch field. It is the type of the boundary. Before I say what kind of it means, we specify the third variable, which is vol mesh. So what these things mean, so before I say, I create the object called U. The purpose was to create a field called U. So this U field is a scalar field. This U field is a field defined over the volumes. So the U values will be saved at the cell centers. That's what vol mesh means. And whenever you have vol mesh, the type of your patch is FV patch field. For example, if it was a field over the cell, over the face centers, it would have been surface mesh. And instead of FV patch field, you would have FVS patch field. So this is the field over cell centers. I hope I think the microphone is very close to my mouth. I hope it has not been annoying so far for you. Sorry if it has been like that. The next step is that, so we have not constructed the object yet. Pretty much similar to the mesh, field is also created from an IO object, an IO object, and a mesh. However, two things. First, the mesh needs to be an FV mesh. It needs to be a finite volume mesh. I will rename this polymesh to mesh 0 and then create an FV mesh from that. FV mesh 0. We could have created FV mesh here directly also. So then this mesh can be fed to the field. This constructor means that me as a field correspond one to one to this mesh. So for cell 1, the first value corresponds to cell 1, the second value corresponds to cell 2, and so on. So this mesh means the correspondence, the mesh that fields correspond to. Then the IO object is pretty much similar to what we did for the mesh. I will go and just copy this. The name of the IO object is U, the field name. Read and write from and into time directories. Register field with mesh. We normally, OpenFOAM convention is that it registers fields with mesh instead of time, because it wants to keep the hierarchy of the data. So the highest rank registry is time, then mesh, then fields. Then IO object, yes, you must read fields, because for example, when you want to start solving the equation, you want to read the initial data and the boundary conditions. You must read it. And whenever you, and then auto write, because we want to write it every now and again based on the control, based on the time controls that we specify in the control dict. So object U is created. Now, the next thing is C2. What is C2? So in order to show another functionality of OpenFOAM that is reading from files, I read C2 from a file. I call it input-output dictionary. I create an IO dictionary and call it wave properties. And actually, IO dictionary gets pretty much similar data like IO object, if I'm not wrong. IO dictionary, yeah, you can create an IO dictionary from an IO object. So this time we decide that the name of the file that is gonna be read from the disk is wave properties. It is the name that you decide what it is. Then where do you read these wave properties from? From constant. So it is constant. So must read and no write. Basically, if you do not specify write option, it is no write, because, well, we don't need to write this dictionary, because this dictionary is something we specified and we read it. That's it. And we register it with the mesh. This is wave properties. And then the next step is that we want to create a dimension scalar called C2. It is a scalar number, a real number, which has some dimensions to keep the dimensional compatibility of the equation. So create a dimension scalar called C2. And a dimension scalar object needs 3 parameters. The first parameter is name. I call it C2. Then dimensions. I know that the dimensions of C2 is dim length squared divided by dim time squared. So it would be power dim length 2 divided by power dim time 2. And finally, the value that this scalar is going to get, we decided to read it from a dictionary. So we say wave properties lookup, and a dictionary, IO dictionary inherits from dictionary class, and dictionary has a method called lookup. It looks into the file and finds the values corresponding to the keywords. Find the scalar whose name is C2. C2. So I divide it into multiple lines to increase the readability. Note that spaces and inters do not have any effect in Do not have any effect in C++. Okay, so the three parameters are given: name, dimension, and where actually the initialization value for C2. Now I think we are good to go, and the code will be compiled. Let me see if we get an error. WMake. So if the matrix is not okay. So you remember that we created an empty options. However, now we have introduced finite volume tools. For finite volume tools, you need to tell OpenFOAM where to look at. Previously, for time, for polymesh, for arglist, that we compiled our code, we scaled our mesh, we had an empty options. The reason was that when you call WMake, it automatically looks into the OpenFOAM library, which sits here. So this is the OpenFOAM library. Inside actually anything here with an empty options, these things are automatically looked up using WMake. So now, however, I need to let me see, jobs. Okay. For options, I need to specify where to look for FV tools, like FV mesh or FV matrix. So all of those things are defined in finite volume library. The first keyword is library, execute. So exe include, which means go search for, I is for include. These are actually G++ options. Form source, finite volume, ln include. ln include is the directory that all of the .h and .c files has a symbolic link there, so that actually this ln include idea, having a directory that includes a symbolic link to all the files, makes it easier for us to find them. This is a smart idea. And then we also need to tell OpenFOAM where to look for the definitions. So all of these things inside finite volume, anything inside foam source is the declarations. Then in order to link our application, our wave foam application, compiler does another, actually WMake does two things. It first compiles our code, then it links our code to the libraries and to the shared so-called, they have different names. They are called shared objects or libraries. So don't be picky on me. I know that in software engineering, every single term, every single of these has very specific meaning. But for actually, when you want to run your binary, your waveform is going to be compiled into an executable. Actually, it gets compiled into an object code. The second step that WMake does, actually the compiler or the linker does, is the linker. What linker does is linking your object code with the shared libraries. So here we say exe leaves those libraries that are gonna be linked to my application. We specify them by option L, finite volume. WMake. When it takes a while, it means that things are going well, thankfully. Okay, so the code got compiled, but actually if we execute it, it won't, it just reads a scalar from a dictionary. We actually want to solve the equation, so we move forward with adding a time loop. So our field, our mesh, and our scalar, everything is being created. Just the last thing that we need to do is to add a time loop while runtime loop What it means is that, so runtime has a method called loop. And what it does is that it, well, as I'm sure that you're familiar with the loops, the idea of loop in general. While something means that do whatever is contained into the curly braces as long as this condition is correct. So runtime loop is the method that looks if the end time is reached or not. As far as the end time in control dictionary is not reached, it keeps doing this, solving the equation, actually creating the equation, and the next step is to actually equation dot solve. Very easy. You can see the power of object-oriented programming. You don't have a huge function here as to how to solve it. You simply call equation solve, and that's it. So, and if we want to write the results to the new time steps based on the actually control dict write controls. The way we do that, we say if runtime write, if the control dictionary forces write at this time based on the write time controls, then mesh write. Mesh write writes not only mesh, but all the objects registered with the mesh. That's why we have the one of the reasons we have the concept of object registry. Let's say we had 70 fields. If you didn't have the object registry, you would have had to write every single field manually. But when you do mesh write, you not only write the mesh, you write all the fields registered with the mesh, just in one go, in one line. So forget about this mesh manipulation, which is from the previous time step. So therefore, if we review what we did, we added a time loop, we create the equation, we solve the equation, and if it is the right time, we write the solution and we go to the next time step. Incrementing time, runtime plus plus, which we had previously, is not needed when you use loop. It is automatically embedded in loop. Okay, so wmake. Cool. The next thing is test. We are going to test our method now. So foam, I clean my test case now. Foam list times, remove the times, and I go to system and decide how often I want to solve my actually what my delta t is going to be and how often I'm going to write the results of my wave equation into the current directory. So I would say the delta t, let it be 1 e minus 3. Let's write interval be I don't know, 100. Let's end time be 50. Stop at end time. Start from start time, although this is optional, and start time is 0. Okay, we are done with control dict. Then in 0, I need a U object. Again, I need foam file. Object is U. Class is volume. Scalar field. I will get back to this. Maybe we can do it now. We might get an error by this. So where we defined our field, OpenFOAM normally does a further pre-processing step. It says that this type name is a bit difficult, so let's rename it to something simpler. It says type def. Type def is a C++ keyword. You define this geometric field, scalar, etc., as a volume scalar field. And then You say volume scalar field U is U W make. Cool. I go to test vim0 U. So after the class, we have format ASCII. And then for a field to be created, you need dimensions. We have 7 fundamental dimensions in physics. The first one is math. So it is not math is 0. The power of kilogram is 0. Our unit is meter because U is displacement. Length, the power of meter is 1. And the power of the rest is 0. Then we have internal field. And the internal field is, let's say, uniform 0. Let's say the displacement everywhere is 0. And then we have boundary field. I will look into my mesh to see what boundaries I have. I have 3 boundaries: moving wall, fixed walls, and front and back. For you, let's say for the moving wall, all of you have, let me see if I have this open. I'm gonna specify boundary conditions, and I want to show you where this moving wall is. I'm pretty sure that all of you have run a cavity case. Okay. Okay, actually, let me finish this first. Jobs. After this, I will show you what's going on here. So moving wall, it is fixed value, uniform fixed value is the type. So type is fixed value, uniform 100. And then for the rest of for fixed walls, type 0 gradient. For the wave equation, I believe 0 gradient means reflection of the wave. However, fixed value means you have this displacement at this specific boundary of domain, the displacement of 100. So front and back is empty. Here we go. I think we are done. So perform. Okay. And I will color my mesh by the patches. Empty, moving wall, and fixed walls. So, this white wall is the fixed wall, which we specified the displacement to be 100. For the red patches, we specified 0 gradient, and front and back, which is green, is empty. The next thing is, so if I run waveFOAM, I will get an error. And the error is, I cannot find wave properties. So I will include wave properties also. Vim constant wave properties foam file. Dictionary. And I specify C2 to be 1e minus 5 for now. And then let's see what happens. So the next thing is FV schemes. What is FV schemes? Because when we discretize this equation, how do you actually, that we have different discretization schemes for time discretization, for discretizing the Laplacian term. You should specify how you're going to discretize. And to do that, we use an existing FV scheme. We don't write it from scratch. Let's go to foam tutorials, fluid. cavity, system, FV schemes, and let's say FV scheme and FV solution into system and FV schemes. We need D2, DT2. We accept Euler. So we set the default to none, and we objectively use D2, DT2 of U to be Euler. And then grad scheme, let it be Gauss linear. Because Laplacian is the divergence of grad, we not only we need Laplacian scheme, but also somewhere in the code we need grad scheme and the divergence scheme also. And for the divergence of C2 and U, and also the divergence of U, I say goes Gauss linear, Gauss linear. I don't need the rest because these are the only two terms that I need. And also, again, in order to have full control of what I'm doing, I set the default to none and set then Laplacian of C2 and U, which we had in the equation. If you remember our waveform implementation, we had this term. So Gauss linear and the interpolation scheme, we need any of the other settings. If we do, we will get an error. So we specify the FV schemes, then FV solutions. We are pretty sure that we will get an error if we don't specify it. We will change P to U. We want to solve the equation for U, and I don't think we need anything else here. I will comment this out. And then we did not use pimple loops, so we don't need it either. So let's see what waveform gives us. It says okay. Maybe I have forgot the semicolon. Div schemes. Okay, let's comment this out. I think it doesn't like space. Okay, here we go. The equation is being solved, and where is my purview? This is my purview. Okay, we just solved the wave equation over this, and I can just to show it a bit more professionally. I will add the filter called warp by scalar. I'm just dealing with these zoom controls all around my screen. You don't see them, but because I'm the host, I see all of those things. So the internal field, where is it? Oh my God. Yeah. First of all, we need to enable the field, and then I'll color the field with U. And maybe I can change the color map to this. Apply. And then you might see that I'm doing nonsense things, but I actually, every place that I click is some zoom control, and I'm not able to do my job. Okay. So the next thing is warp by scalar. I want to warp this by scalar, but warp is not enabled for some reason. That's strange, actually. I don't know, maybe I need to reload it. Yes, warp by scalar. So actually, if I scale it down to, as you remember, our, let me show you the surface with edges. As you remember, we specified the only wall called the moving wall, we specified the displacement at that boundary to be 100, and everywhere else the displacement is 0. So I'll reduce it to some factor. Cool. And I play the animation. So this is, as you can see, the 1D wave. So this is the propagation of the 1D wave. It can be 2D if we specify the okay. So it can be 2D. To create a 2D wave, I'll do something else. I'll foam this times Rm. I can do actually set fields. I want to, if I go back to the initial test case, you can you can set the fields, set the value of u at the center of your domain to 100 and keep your boundary as 0, and then let this disturbance diffuse through your domain. So I think I have this test case in another, I just show you because I'm not sure if we have time to do that here. Yeah, maybe it's handier for me to just show you. Push the so if I just go run and parafoam, so we are actually reaching to pretty much to the end of the session in 7 minutes. So I just want to show you that how that 2D wave works. I think I don't have you here, so let's enable you and let's warp by scalar, and let's decrease the amplitude by factor of 1,000th. Okay, we have a perturbation at the middle, and then when we play this, the wave propagates. So what is different in this test case compared to what I just showed you is that in my system, I have a set fields dict where I have decided to, I have set a box in the middle of the square, and I decided that the value at that box to be 100, and then the rest of the boundaries are 0 gradient, and then this simulation causes such a wave propagation. Okay, guys, we are done with our session. I think 2 guys are in the actually, what is it called? The waiting room. And for some reason, I do not have access to the waiting room anymore. I'll have just some extra information to give you in the remaining 5 minutes. First of all, thank you for coming down to this event. I think, yep. So there is an example in So for 1 second, I saw that nothing was shown. Uh, excuse me for too much of interruption. I had a nightmare on my screen for a moment. So in the slides, we have another example of a heat equation that, if you like, you can have access to the wave equation and see how it goes. Also, as the next step, as you saw, we had a few actually quizzes in the slides. The quiz for the rectangle, writing a rectangle object, writing a rectangle class, the quiz for writing a random mesh class and creating an application that randomizes meshes. And finally, we also have an assessment task, which is a minimal surface PDE problem that, if you guys would like, you can do that and submit your results, and we can have a chat about it. And in case you can successfully do that, you will get a certificate from TensorFields. The next step, regarding the material of this presentation, I have already sent you a link. The link is not active yet, but it will be activated in 24 hours. And just in case, I will send you another email. And that's all for today. Thank you everyone for coming down. We plan to continue for, if we can, on a monthly basis. But we are really interested to. I'm especially really interested in knowing your feedback as to how it was and how we can improve it. I'll stay here if anyone wants to chat for maybe 10 minutes, but the session is officially done. Thank you very much.
Thank you, Ali. It has been lovely to see you hopping on the editor.
Thank you, man. Thank you.
By the way, do you have any plans to do some tutorial on, let's say, CHT, conjugated heat transfer solution, since you have a couple of different domains in the mesh?
Well, we can discuss it if you like.
I don't need it, but just dropping down ideas.
Yeah. Actually, it is. It is not the focus of what I do, but I'm really interested to work on different physics. So yeah, maybe not. I mean, why not? If there's an interest, for example, if there's a project that is offered that I need to work on conjugated transfer, yeah, definitely I will. Or if there's a training need for that, yeah. But just if we decide to do that, you will be informed either through the LinkedIn or on the website. Yeah. Okay, guys. Thank you very much. Don't forget that have a look at our website, tensorfields.com. There is a tab called Products, and in Products there is Meeting. And well, basically, I'm not an important person, therefore you can book a meeting for free so that we can chat about if you have training needs or if there's something regarding OpenFOAM that you just want to talk about. So I'm happy to engage in a conversation in that regard with you. I will end the meeting for all.